Hi, my name is Suyang Bae. I'm going to present my recent accepted paper named Salad, Improving Robustness and Generalization through Contrastive Learning with Structure-Aware and LLM-Driven Augmented Data. Before start presentation, I'm going to introduce my lab. I'm studying at IIS Lab, and my advisor is Jiyoung Lee. In our lab, various types of research are being conducted, including computer vision, natural language processing, multimodal AI, and lightweight AI. Recently, we have been conducting hot trendy research topics such as diffusion model, LLM model, multimodal model, and lightweight model. Also, in our lab, there are some events in a year, including conference workshop, OBYB football match, and AI challenges. Door of our lab is always open, so anyone interested in our lab can come in anytime. To introduce myself, I am Suyang Bae and I am now a PhD student. I usually have studied robustness and trustworthy techniques in NLP fields. My recent interests are as listed below, like robust trustworthy AI, bias hallucination mitigation, AI ethics or morality, and recently I am studying about factual consistency in code summarization and evaluation, and multi-agent code documentation tasks. And my recent publications are as follows. And if you want to see more publications or activities about me, please visit my website. From now on, I'm going to introduce my paper. My presentation is proceeded as follows. This paper is aimed to address the spurious correlations in various NLP tasks. Spurious correlation occurs when two variables appear strongly related, but there is no genuine causal relationship. This problem of spurious correlation causes poor performance, especially when handling out-of-distribution data. Let's assume that we use a movie review dataset for sentiment analysis. The dataset frequently mentions the famous director Spielberg in a positive context. During training, the model observes many positive examples associated with the keyword Spielberg. The model therefore mistakenly learns a shortcut that word Spielberg is closely related to positive labels. This shortcut is learned regardless of the actual sentiment expressed in the sentence. Therefore, when a trained language model encounters a sentence mentioning Spielberg, it incorrectly predicts a positive sentiment, even though the correct sentiment is negative. Therefore, when a trained language model encounters a sentence mentioning Spielberg, it incorrectly predicts a positive sentiment, even though the correct sentiment is negative. One method to address this spurious correlation is data augmentation method. Data augmentation has traditionally been used to improve model performance and increase data diversity. However, they had the drawback of lacking fine-grained control over the quality and relevance of the generated data. Therefore, the method of counterfactual augmented data has been devised. Counterfactual data augmentation is a method for adjusting dataset label balance by intentionally flipping labels through minimal word modifications, thus generating counterfactual examples. Typical methods of creating counterfactual augmented data include by using human-generated, rule-based, or LLM-based automatic generation. However, each approach has its limitations. First, human-generated methods cause high cost and time-consuming. And second, automatically generated methods require careful tuning to maintain context and meaning. Moreover, most current approaches focus only on data augmentation, neglecting the need to enhance model robustness during training. To reduce shortcuts while improving model robustness, it is necessary not only to focus on contextual patterns, but also to learn structural patterns where shortcuts occur. Models that learn these structural patterns can capture the fundamental meaning of sentences and the relationships between key components, rather than relying on word frequency or specific terms. By doing so, the model effectively avoids shortcuts and achieves stronger generalization. In this paper, we tried to learn the causal relationships within sentences to effectively learn structural patterns, rather than just word frequency or simple textual features. This allows the model to focus on important words such as nouns, verbs, adjectives to grasp the core meaning of the sentence, while reducing its reliance on less significant words such as pronouns, conjunctions, like that. Consequently, models that learn structural patterns can provide consistent performance across a variety of sentence structures. So in this paper, we propose a new method named SALAD, which combines structural-aware augmented data generated by a tagging-based approach that considers structural patterns and counterfactually augmented data generated by large language models to create complex and diverse sentence patterns. Then, contrastive learning is applied to effectively capture key sentence structural patterns between our augmented data. Our SALAD helps the model effectively learn key patterns in simple sentence structures, reducing its dependence on shortcuts. Simultaneously, the model learns negative patterns in various contexts, enhancing its generalization performance. So, we propose a method to construct positive data that reduces bias from non-causal words and spurious correlations, enhancing model robustness and generalization. It consists of two steps. First, we leverage the part-of-speech tag set to identify structural information where shortcuts are likely to occur. Then, we construct a non-causal POS tag set G. Second, we generate positive sample by masking random K non-causal tag words in the original set. First, given a collection of training data and the universal and the universal POS tag set, we first remove all words corresponding to each POS tag. We then calculate the average accuracy reduction from the standard fine-tuned model to determine which tags are irrelevant to the label. Then we iteratively calculate the average accuracy reduction for each POS tag set in the dataset. So after calculating all average accuracy reduction, if the average accuracy reduction exceeds a threshold, we consider that the corresponding POS tag is a causal POS tag, meaning it is directly associated with the label. Conversely, if the reduction is smaller than the threshold, we assume that the corresponding tag set belongs to the non-causal POS tag set, indicating it does not affect the label. After defining the non-causal POS tag set G, we randomly select K tokens from each sentence that belong to G and replace these tokens with the unknown token, constructing a set of structure-aware positive data. And second, for constructing counterfactual data, which means the negative pair, we use LLM to incorporate not only structure-aware data, but also diverse sentence patterns. We provide additional word information corresponding to the causal POS tag set in the prompt, minimally altering genuine tokens that directly impact the label. Finally, we use contrastive learning for effective training of models in the generated counterfactual and positive data. First, the counterfactual data generated by altering only genuine tokens using LLM are considered not only to be a loss for direct label prediction, but also to be a loss that encounters them to move further away from the original sentence in the latent space. Next, by bringing the positive data closer to the original samples in the representation space, we effectively mitigate bias towards non-causal words and enhance the model's generalization ability. To validate the ability of our method to address the phenomenon of being biased by spurious correlation in training data in various tasks, we conduct experiments on 3 tasks: sentiment classification, sexism classification, and natural language inference. We trained the model using the original training data for each task and evaluated the model across various settings, including in-domain, out-of-distribution, and cross-domain environments. We compare our proposed method with various text data augmentation methods, such as EDA, Samba, and ArcGPT, and 2 counterfactual data augmentation methods named Human Counterfactual Augmented Data and Core Counterfactual Augmented Data, and robust learning method, such as SubCon and C2L. As shown in 3 tables, Salad demonstrates improved overall accuracy compared to standard fine-tuning baseline across all tasks, while it shows a slight decrease of about 1.16% compared to human CAD in the sexism classification task, making it the second best. Salad achieves the best performance in all other tasks like sentiment classification and natural language inference. This indicates that our method is robust and performs similarly to human-generated high-quality CAD, even surpassing it in the sentiment classification task. Specifically, Salad is particularly effective in out-of-distribution scenarios. While human CAD achieves the highest performance in domain distribution due to the use of counterfactual training during training, its performance on out-of-distribution data is consistently lower compared to Salad. This underscores that the proposed method, Salad, significantly enhances generalization capabilities and ensures model robustness, leading to a dramatic improvement in overall performance. For the performance of the cross-domain task, there is a substantial increase in performance, with the overall accuracy reaching 91.61% in six cross-domain settings. The efforts to address spurious correlations in Salad can potentially contribute to improving generalization abilities, even when the domain undergoes a shift. And additionally, we evaluate our generated LLM-based counterfactual augmented data in three metrics: word diversity, overlap, and context similarity. As a result, GPT-CAD used in our method demonstrates performance close to human CAD, particularly with a BERT score and diversity. This highlights the effectiveness of our LLM-driven counterfactual data generation compared to manually generated data. GPT-CAD used in our method effectively preserves the original sentence structure while changing only a minimal number of genuine tokens, outperforming previous methods in terms of both structure preservation and context. So, as conclusions, in this paper we introduced Salad, a method that enhances model robustness and generalization through the use of structure-aware and counterfactually augmented data for contrastive learning. These results highlight the potential of our approach to address the challenge of spurious correlations in natural language processing, providing a more robust and generalizable solution. So thank you for listening my paper. And if you have any questions, feel free to contact me via this email. Thank you.